Hi guys, we will derive what I believe to be the most important equation in mechanics of materials, and that is the Flexural formula. Welcome to part 1 of the derivation process to the Flexural formula. What is the Flexural formula and why is it so important to know? The Flexural formula is basically sigma, which is stress, is equal to minus my over I. Now sigma is the internal normal stress, compression or tension. The units for stress is MPa, Newton divided by millimeter squared. So basically it is force divided by area. So in a sagging beam, the maximum compression is at the top of the beam and maximum tension is at the bottom of the beam. M is the internal moment due to the applied loads at the location along the beam where we want to determine the stresses. Say for example, we have a 5-meter long beam and our lovely steel fabricators just went ahead and did a hole in the steel beam at about 1.2 meters from the left, and we get this problem all the time. So to determine the normal stress distribution at the location of the hole, the internal moment M, in this case would be 40 kilonewton meters and not the maximum moment of 60 kilonewton meters. You can use 60 kilonewton meters, however this would be absolutely conservative. Y is the distance from the neutral axis to the location we are interested to know the value of the stresses. So for a sagging beam, we can determine the compressive stress at any location above the neutral axis, and the value of the tensile stresses would be below the neutral axis. In most textbooks, you may notice that there's a negative sign in front of the my over I. A negative or a positive sign all depends on the initial sign convention you assume for the direction of y. All a negative represents is that the beam is in contraction. So in the compression zone, you will find the value to be negative. So if you take y up as being positive, then this means the compression strain at the top of the beam is taken as negative value. If you take y down as positive, then the compression strain at the top of the beam is a positive value. I guess we will discuss this more in details in the upcoming slides, but either way, the most common sign convention is generally taken as y up being positive and y down is a negative value. I is the second moment of area or moment of inertia. It is basically the section property which helps to resist bending. So it's a measure of the section ability to resist rotation about the major or minor axis. To accurately understand beam design and strength of materials, it is very important to first visualize the mode of failure and the stress developed in the beam that causes that failure. Let us first start with a quick demonstration of a beam design utilizing the importance of Flexural formula. Here we will get a better appreciation of why it is important to understand this formula. We have a 6-meter long prismatic steel beam, 400 deep by 100 wide. The beam is simply supported with 100 kilonewton point load at the midspan. The maximum bending moment is 150 kilonewton meters, which is just basically PL divided by 4. The moment of inertia is 5.3 times 10 to the power 8 millimeters to the power 4. And Y, which is the distance between the neutral axis and the compressive face of the beam, is 200 millimeters. The calculated maximum bending stress, my over I, is about 56.3 MPa in tension and compression. Say we are given a steel yield capacity of 250 MPa and we are using a conservative factor of safety of 3, which is probably very conservative. We will then get an allowable bending stress of 83.3 MPa, which is 250 divided by 3. And that is greater than the applied stress of 56.3 MPa. So it is important to understand flexural formula to have a better appreciation of material strength and capacities with respect to the applied load, strength, and the geometry of the beam. Here we have the same beam on a finite element program using shell element, which demonstrates the shape of the bending stresses contours and the associated deflection. You can clearly see the shape and color of the contours throughout the beam section. At the midspan, where the moment is the greatest, we have about 56.3 MPa in tension. This is the dark blue zone, and minus 56.3 MPa in compression, the magenta zone. Or we can say an absolute value of 56.3 MPa. The yellow zone is where the neutral axis passes through at the geometrical centroid, and therefore we don't have any flexural stresses in that zone. We could also see that the maximum central deflection is about 4.2 millimeters in the tensile dark blue area, which is a lot less than the allowable deflection span over 300, which is about 20 millimeters, 6,000 divided by 300. Or even if we take it as 10 millimeter deflection, we are still within the limits. We should also check the applied and allowable shear stress. However, I guess I'll leave this to another video. Okay, to begin the derivation, let us consider an isotropic homogeneous prismatic beam with global axis X, Y, and Z, and it has a length L. The neutral axis passes through the geometrical centroid as shown here. When a load is applied onto the beam, it deforms through the beam about the Z-axis. The shape of the bending usually follows a shape of an arc, as you can see here. Now, due to the external loads, there must be internal stresses developed in the beam to maintain equilibrium, force equilibrium. If we cut the beam as it is deforming, we will see internal shear and bending stresses. You can see here in the 3D image, there is a shear force as a resultant of the vertical shear stresses acting parallel to the cross-sectional surface, and we will also see an internal bending moment, which is the resultant of the normal stresses known as bending stresses, and this acts perpendicular to the cross-sectional surface. The normal stresses here are referred to as tension and compression, and they are acting opposite to each other. Let us focus here for a second on bending stresses, particularly in the context of pure bending. Imagine the beam as a collection of small fibers. The top fibers compress or contract, and the bottom fibers are in tension, which extends. The normal stress will act linearly, eventually creating a neutral surface that remains unchanged throughout the length of the beam, and this is because we have one side is in compression and the other is in tension. This neutral surface passes through the geometrical centroid of the cross-section, and it is referred to as a neutral axis. So bending stresses at the neutral axis would be zero, while shear stresses would be maximum. To work out sigma, the bending stress, and to start deriving it, we need to first calculate the strains in the beam due to bending. So this is the first part of the derivation, and to start this process, the first thing we need to look at is the beam before and after bending. Let us look at the before bending diagram. We will take, in this case, we will take y up as positive. Then we will look at a small segment. Let's take a small segment of the beam and call that delta x. The dashed line here denotes the neutral axis, and we have shown another horizontal line at a distance y above the neutral axis in the compression zone, and we call that delta s. Then at either ends of delta s or delta x, we have shown two vertical lines. the whole aim here is to study what happens to points A, B, C, D, E, F, G, and H between the vertical lines, delta S, the neutral axis, the top of the beam, and the bottom of the beam, before and after deformation. These are the main important planes that we need to study. Now, let us look at the after beam bending diagram. We can see that the vertical lines here at the ends has only rotated. Let us go to a zoomed image, which is a lot clearer. Here we go. There are 5 main observations I would like to discuss with you here. 1, you can see that the vertical lines, points A to G and points B to H at either ends has only rotated at a particular angle. However, it still remains straight. What we do notice is that there are no deformation in the vertical plane, but only rotation. The assumption here is, and you've heard this before several times, the assumption here is that there are no shear deformation in pure bending. This implies that plane section before bending remains plane after bending. 2, the top surface of the beam at points A to B has compressed or contracted to A-B'. You can see here how the ends have compressed and the vertical plane. From the vertical plane, you can see the compression here at either ends. The top surface of the beam experiences the maximum amount of compression when the distance y is equal to SC from the neutral axis. 3, the plane delta S at point CD has also compressed to delta S dash, which are at point C dash and D dash at a distance y above the neutral axis. 4, the neutral axis plane EF to E-F' has not changed. As you can see here, there are neither compression or tension. So the point E is equal to E dash and point F is equal to F dash. The points here have not shifted after bending, and this is why we call it the neutral axis. 5, the bottom of the beam, GH, has clearly extended to G dash H dash due to tension. So any planes below the neutral axis deforms by tension, which extends the beam, and any planes above the neutral axis is deformed by contraction due to compression. Now let us take this beam segment, at the ends, and extend the rotated lines to meet point O. O here is called the center of curvature, while R is the radius of curvature. And the radius of curvature is basically the distance between O and the neutral axis at point E dash or F dash. So the distance between delta S dash at point C dash to the center of curvature O would simply be R minus Y. Firstly, because we have small deformation, we can say delta X is equal to R theta. And guess what? Delta X is also equal to delta S, which means that we can rewrite delta S to be equal to R theta as well. Now, secondly, delta S dash would then be R minus Y, which we worked out before, times theta. Now we are ready to establish a relationship for the normal strain that occurred in the beam due to bending at a distance y from the neutral axis. The equation of this strain, if we all remember, it's the final length minus the initial length divided by the initial length. So we have epsilon, this strain, is equal to delta S dash minus delta S. Now delta S dash is the final length, minus delta S, the initial length, divided by the initial length delta S. So we can already see here why the answer would be negative, because delta S dash is in contraction, it's a lot shorter than delta S. We can rewrite the above strain relationship in terms of y and the radius of curvature r, and say E epsilon is equal to r minus y theta minus r theta divided by r theta. All we did was just substituted delta S dash and delta S. If we expand this equation and work it out, all the thetas will cancel out, and then we would be left with epsilon is equal to minus y divided by r, and we will call this equation 1. This is one of the most important equations and is part of the first derivation of the flexural formula. With r being constant, then this means that the strain is shown to vary linearly over the cross section, and we also have shown that at a distance y above the neutral axis, this strain is a negative value because there is compression or contraction. So this ends the first part of the derivation. Please join us on in the second part of this derivation in the next video. In the meantime, we hope you found this video enjoyable and helpful, and have a great afternoon.